In this second video for 13.3, when we're taking partial derivatives, here we'll be looking at higher order partials, really only looking at second order partial derivatives. It's almost the same thing as like a second derivative. Just in this case, when we're looking at a function defined of several variables, if we take f that's defined as a function of x and y, the first partials we take, one's with respect to x, the other's with respect to y. So when we take second partials, or similar to second derivatives, we have more potential outcomes here. It's not just, oh, we take a second partial with respect to x, or a second partial with respect to y. Those are options. There's also what we call mixed partials. So I'll go through each one of those. And we remember this whole time that when we're taking a partial derivative with respect to one variable, we leave all other variables as constants. Okay, so I'll try to outline that as best I can in these examples here. Setting up just the notation here first, the second order partial with respect to WRT, second order partials here. The second order partial with respect to x, I'll do in green, WRT with respect to x. What we do here is we take a second partial with respect to x. So from the partial derivative of x, we take another, right? So I've got the first partial with respect to x, and then I take another partial derivative, okay? So this is, order of things does matter here. The way we write this is similar to how we would write a second derivative. We do a partial squared of f, partial x squared, okay? And shorthand, in the subscript notation, we would write that as f subscript xx. So for the second partial with respect to x, in that subscript notation, it's doesn't really matter which partial with respect to x you're taking first. You're taking two partials with respect to x, okay? That's kind of a logical first step, and we will often write that as f subscript xx. The next, I'll do the second partial with respect to y, and that'll be in blue here, and I'll continue that trend when I do an example. Second partial with respect to y. So that takes a partial with respect to y of the first partial with respect to y. Partial f, partial y. Okay, so this second partial is two partials in a row with respect to y. Then I write that as partial squared f, partial y squared, or f subscript yy. Okay, so these will come up. They have a similar meaning to concavity, but it's specific to the direction that we're talking about here. So it's not just a regular second derivative, right? It's a second order partial. It's a bit different, and it has some slightly different meaning, but along the same lines. We also have what I alluded to before, mixed partials, okay? So that's when we kind of change the order of things. If I take a partial with respect to x, and then a partial with respect to y. So that's a mixed partial. A mixed partial, we say, with respect to x, then y, is we take the partial with respect to y of the partial with respect to x, having been done first. Okay, so the order of things matters here. When we write this with our partial squared notation, we have partial squared f. From left to right is kind of the opposite of the order that things happen. So I'm stacking things kind of from right to left. We take the partial with respect to y of the partial with respect to x. So in terms of order, we took a partial with respect to x and then a partial with respect to y. In the subscript notation, this would be f subscript xy. So in this notation, things make maybe a little more sense. And actually, I mixed up the colors here. I apologize. But x should be in green there. There's your order. I took a partial with respect to x and then a partial with respect to y. Okay? Same idea for the next mixed partial, but this time we're going to take the partial with respect to y first and then a partial with respect to x. Let's see, I did it again. So this should be partial with respect to, switch the order of these things, partial with respect to y, and then a partial with respect to x. I'm sorry about that. So in this case, we'll take a partial with respect to x of something that we've already taken a partial with respect to y of. So that's correct there. So what I see then is a partial squared f and partial x, partial y. Again, that should be a y there. That should be a y, and y's were in blue. Again, I apologize, my color scheme got a little messed up. And in subscript notation, this one I should have correct here, is f subscript y, then x. Oops, sorry. Go back. Okay, so this is how we'll denote partial derivatives. Similar to what second derivatives gave us in Calc 1. They gave us concavity. We had a second derivative test, right? So we were able to determine if we had a maximum or minimum value based on the second derivative at that point. There's a similar second derivative test for functions with multiple variables, and all of these will be used in that test, right? You'll get more info about that as you get on to Calc 3. So I want to do an example where I find all of these second order partials. So all of these are second order partials. Even the mixed ones are considered second order partials, right? They're just mixed. So in this example here, I have f of xy is arctangent of y divided by x. Find the second order partials. So I wanted to do one that had kind of a couple components, maybe some chain rule, some quotient rule, some things going on here. We have to remember the derivative of arctangent of something. Okay, so first what I'll do is I'll take the first partial with respect to x, right? And we can just use this subscript notation. That's nice enough for us here. When I take a partial with respect to x, I take the derivative of arctangent of something, and we remember that y is a constant, right? And I'll talk about that as I get to the argument. But basically, the first derivative, or the derivative of arctangent, should be 1 over 1 plus the argument y over x, quantity squared. Okay? That's the derivative of arctangent of something times the derivative of the something, or the partial derivative of the inside y over x. Okay? Since y is a constant, I'm taking a partial with respect to x of, how would I take a derivative of a constant over x? Well, I'd have to bring the x up to a -1 power. So I'm going to try to outline, when I'm paying attention to a specific variable, I'll outline that in the variable's color. So here I'm treating, anytime I'm looking at actually taking a derivative or a partial of x, that should show up in green. Okay, so this chain rule, because there's an x in the argument of arctangent, I have chain rule here, and the derivative, or partial derivative of y times x to the negative first, I treat that like a normal derivative with respect to x. Okay, y is a constant. So I keep this quotient the same. I'm going to square y and x here. Multiply that by, when I take a partial with respect to x, that should be minus y times x to the -2, or x squared in the bottom, right, in the denominator. Okay, that's the derivative of x to the -1 with respect to x. Simplify just a little bit, because I need to take second partials from the first partials. I want to try to have simplified first partials. Okay, so I'm gonna multiply across the top and across the bottom, distribute the x squared across the denominator, and I see with a -y in the numerator, then I should have an x squared plus y squared in the denominator. Okay, now I'm going to have to take another derivative of what's in that pink box there with respect to both x and y, right? First, we'll do things with respect to x. So let me rewrite this. Here's my first partial with respect to x. It's that guy right there. But also, I might want to treat this, right? I have an x in the bottom. The only x I see is in the denominator. So what I might want to do is bring that denominator up and have it written with a negative first power. Okay, so I'm going to use maybe that to my advantage because the x that I see here, x, that's the only variable when I take another derivative with respect to x, and it's in the denominator. Okay, so when I take a second partial with respect to x, what's going to happen is really I'm going to look at this second form here, and I'm going to bring that -1 power down because I have my variable x plus that y squared. That's a constant. So really what I have is x squared plus a constant squared, all to the negative first power. When I take a derivative, I bring that -1 down, and that's where I see that the green, positive sign. Y is a constant. It just stays there out front. Times the inside, x squared plus y squared stays the same. Subtract 1 from the power, I get a -2. Chain rule times the derivative of the inside, the partial derivative of x squared plus y squared with respect to x. That should give me I'm just going to write it, x squared plus y squared with respect to x. In green is the variable that I'm paying attention to. Take a partial of that with respect to x, I get a 2x when I multiply. 2x. Okay, which of course simplifies to this guy right here. 2xy in the numerator, just slide that 2x on top, and x squared plus y squared, quantity squared, in the denominator. Could I have used quotient rule here? Yes, absolutely. But the partial with respect to x of the numerator, low d high, partial with respect to x of -y would have been 0 because there's no x in the numerator. Okay, so there's just a little bit of weirdness, but as soon as you get used to leaving all the other variables as constant, you'll get more comfortable. Now we're ready to take a partial with respect to x, then with respect to y. So this will be my mixed partial here, fxy. I'm going to try to outline in blue what I have to pay attention to. So from my first partial with respect to x, I see a y in the numerator and denominator. That implies that I should be using quotient rule. So I've drawn my quotient sign there in blue because I'm looking at y's as being my variable now. And since there's a y in both the numerator and denominator, that means quotient rule. So I'll leave the negative out front, and I go through my quotient rule, like low denominator times the partial with respect to y of the numerator. Derivative of y with respect to y gives me a 1. Less, minus, high, d low, partial derivative of the denominator with respect to y. Partial of x squared with respect to y is 0, plus partial of y squared with respect to y is a 2y. Draw a line and square below, x squared plus y squared squared. Simplify a bit. When I multiply through here, I end up with x squared plus y squared minus 2y squared, and there's a negative out front of the whole thing. All right, divide that by x squared plus y squared squared, and then I end up y squared minus 2y squared is a negative y squared. If I bring the minus sign in, I can change the order. The y squared would be negative, multiplied by a -1, it'll make it positive in the numerator, y squared, then minus x squared. Okay, so like I said, things are a little weird, a little tricky at first here when we're taking second order partials especially, but as you do more examples and more practice, they should work themselves out. Okay, I'm going to go through and find the first partial with respect to y, and then find the second order partials that involve y. So these two here are the first two second order partials. I need two more. So here's my function. Find the first partial with respect to y. Okay. Partial derivative of arctangent with respect to y should be that 1/1 plus the argument squared. Chain rule times a partial with respect to y of y over x. Okay. X is no longer my variable. Y is my variable. I'm taking a derivative of y over a number. Derivative of y over a number is just the fraction 1/x. So what I see is 1 over 1 plus y squared divided by x squared times just 1 over x. The derivative of y with respect to y is 1, and x is a constant. It just comes along for the ride. Okay, so I'm going to do a little bit of algebra here. I'm going to find a common denominator down here and then multiply through by x, and I end up with x divided by x squared plus y squared. Okay, so that I'm going to have to take another partial derivative of with both respect to x and y. And I'm going to do another rewrite because depending on the derivative I take, I might want this as a quotient or I might want it as a negative exponent. So the first partial with respect to y is exactly what's in that orange box, but I can also treat it like x times x squared plus y squared to the negative first. Okay? So when I take a second partial then with respect to y, what I look for is that there are y's, only y I have is in the denominator. Only y I have is in the denominator. So that means that I do not need quotient rule when I'm finding fyy. All I need to do is look at the right form here, this form, and take a partial with respect to y. X is a constant out front. Then I have a constant plus y squared all to the negative first. I bring the negative one down. X times, inside stays the same, x squared plus y squared. Subtract 1 from the power, I get a negative 2, times, chain rule, 2y is the partial derivative of y squared with respect to y. Partial derivative of x squared with respect to y is 0. Simplify a bit. I'm going to bring x squared plus y squared to that negative exponent down to the denominator, and a negative 2xy left over in the numerator. There's the second order partial with respect to y. Okay. All that's left is my mixed partial, my partial with respect to y, and then x. Okay. What I notice from the first partial derivative with respect to y, I have an x in both the numerator and denominator. This needs quotient rule. Okay. Yes, I could technically do product rule with that second form here by looking at that x and that x. I just choose quotient rule. I think it's a little bit easier to work with and simplify, maybe a little bit easier to spot. So I go through my quotient rule. I see low x squared plus y squared, d high. Partial derivative of the numerator with respect to x gives me a 1, minus high, the numerator, times the partial with respect to x of the denominator. I see a derivative of x squared with respect to x. That gives me a 2x. And the derivative of y squared, partial derivative of y squared with respect to x is 0. So the only thing that shows up in the less high d low derivative of the denominator is a 2x. Draw a line, square below, x squared plus y squared, quantity squared. And again, in green there, I have what I would have from the quotient rule, right? Basically, because I was taking a partial with respect to x here, I needed to use quotient rule, so that's why I've drawn that quotient in green, because it pertains to that variable. Okay? Simplify, x squared plus y squared on top, and I'm subtracting then 2x squared. This guy here would be a 2x squared from x squared, which gives me 2x squared, y squared minus x squared, divided by that denominator there. And I am done. This guy then is my second order partial with respect to x, my mixed partial with respect to y, then x. And if you notice, if you go back a slide here or go back in the video, what we really have, that's the same thing as the other mixed partial. That's just about always going to happen. Those two should always be equal. So you know you've done your mixed partials correct if they are the same. At least in any examples I give you. I imagine we could cook up some that aren't quite the same, but For the most part, those two are going to be equal, and you will talk about that a bit more in Calc 3. Really, for Chapter 13, this is all I need to show you. Okay, the rest will continue on, like I said, in Calc 3. But as long as you can take second order partials, I've only done one example here. It took me 20 minutes. I would be happy to work through some more examples with you, but you have some options there. Make sure to do some practice problems. Otherwise, thanks for watching.